Okay, so one of the things that I wanted to show you, now is it recording or is it not recording? Yes, it's recording. So I am still grading, so that homework assignment won't definitely be due until a week from Friday, but hopefully I'll get all my grading back to you soon, just doing what I can. If in the meantime, if you want to see a key at least to the one that I'm currently grading, that's available. Couple of things about that assignment was really like long, and so as a result it's taken me a long time to grade it. Did you guys feel like that assignment was a little long? Yeah, it was long. And I just have to say, you know, it's my first time teaching the class. It sort of didn't strike me quite how long it was, but I like it and I'm glad that we've done it, but maybe I could have broken it into two, that's all. So as a result, you got that done now and you're kind of getting some free time now. All right, so anyway, but I don't know what to say except I'm sorry. You know, I don't know things, my past self does not know things that my current self knows. So I apologize for that. All right, anyway, we can go ahead and get going unless there are any other questions today. All right, Rodney, would you hit the light? This setup is so weird. I'm really supposed to stand right here and write like this. I don't know why anybody would have done that. But whatever. All right. Let's go ahead and get started. Last time we left off, let me pull up my note from last time. And we were talking about expressions for potential energy. And we were doing the example. So one of the things that we'd already found that the potential energy associated with a conservative force is negative of that conservative force dot dx from some place where we're calling energy 0 to some place where we'd like to know the energy as a function of location. All right. And then we also found that once you have an expression for potential energy as a function of location, you can always find the expression for that conservative force by taking partials. So we were kind of testing that idea out. And I was doing that with the gravitational force. And we'd gotten an expression for the potential energy associated with gravitational force. And then we were going to find the expression for the gravitational force and make sure that we got our thing back that we had originally. So let's go ahead and do that now. Okay. Are you watching a lot of baseball these days? Are they still in or are they out?
Yeah. The Cubs lost last night, so
That's
I'm happy.
you know what, I sort of feel like either way is fine. I feel bad for the Cubs, but being from St. Louis, I don't like the Cubs, so either way.
Or are we doing like I'm going back?
You're finding FG to check. See if you get your original. From this, you're finding FG.
Okay.
Okay, your first line should be FG is equal to partial of U with respect to something, with minus sign out front and a question sign above. When my work, I went ahead and used the point where the mass that I'm interested in, its location is defined as the z-axis, so I could just use this, in which case see if I get that expression back that I started with. Go ahead and start working it then. So is this equal to the minus partial with respect to z of the expression that I found here, which on the z-axis, for particles on the z-axis, boils down to minus g mm over z. So let me start the new page for today. And this will give me my zth component, I guess. All right, so I've got two minus signs. That'll give me a plus sign, partial with respect to z of g m m z to the minus 1, which is equal to g m m. I'm going to give you guys a moment if you haven't gotten there to finish that. Okay, so what do I get for that derivative? What do I get? Let's finish up my line here. What comes next? Who's got something I can look at?
Over z squared?
It's a power rule, so what is it? What is it? Just somebody say what it is.
Times minus 1
Times negative 1, very good.
times z to the negative 2.
Times z to the minus 2, very good. All right.
Over z squared.
Which is the same thing.
So I come back to my original expression, and it does indeed check out. All right. So good enough. Let's be done with that. Cool. I have enough space up here today. We took my big table. All right. So let's go on and pick up from there. So the next thing we want to talk about is something that's sort of different. But now, I mean, just to summarize what we did last time, we've already figured out how to find potential energy for a conservative force. Now we figured out that if you have potential energy, you can also get the form of that conservative force that way too. And now we're going to talk about time-dependent potential energy, which sounds like an oxymoron, and it pretty much is. All right. So sometimes we have a force that is a function of location, but is also a function of time. And if that force has zero curl, then we still have that sort of path independence thing. So we kind of have a lot of the characteristics of a conservative force, except that we don't have them all. So let's just go ahead and note that. All right. So what I'm talking about is, on occasion, sometimes, there is a force that is a function of not only location, but also a function of time. Now that is a problem because in terms of our first characteristic of conservative forces, it's already violated. Right? Okay. But this force is kind of intriguing to us because its curl is zero, meaning that we will still have something path independent that will be, therefore it can be described as a function of location, but it won't exactly be a potential energy, but it's going to be a lot like a potential energy. So we might be interested in looking into this type of situation and see what we get. So anyway, let's go ahead. I think I've said everything I need to say about that. It meets the first condition, but not the second condition. And it kind of almost meets the first condition because it only misses by this time dependence. All right. So in this case, what we are going to choose to do, because we do have this thing that's a function of location, because we have that path independence thing, since there's no curl, we're going to choose to think that we're going to say this thing has a potential energy. But the system is not going to be isolated energy-wise. So it'd be kind of weird. So what that means is that we will let there be something that we're going to call a potential energy. But the potential energy is not going to be, since this isn't actually conservative force, we do have this function of location that's curlless, this thing that's going to be path independent, so we're going to choose to call that potential energy. But in this particular situation, the mechanical energy, which is equal to the kinetic energy plus the potential energy, will not be conserved quantity when this force is acting. So this thing that we get for potential energy won't be constant. So what is it going to be? Let's see what it's going to be. All right. So we're going to go ahead and think about, since I've chosen to say we're going to call this thing that's not path dependent potential energy, let's go ahead and calculate potential energy. Put that thing out of the way. All right. So what I've got for my expression for potential energy, it's going to be the same old thing that it's always been. So it's negative the line integral from wherever I'm calling potential energy 0 to my point that the object is at, f of r and t dotted with dr. And your author, whenever he has a definition like this, and r is also one of the limits of integration, he chooses to make an r prime within the integrand, just to make it clear. I don't know if we need that. I think it's fine this way, but okay. All right, so we have this expression, except that we have an issue because this force here depends on x and y and z and time. So not just x, y, and z. And what that means is that an incremental change in potential energy can be expressed as the partial of u with respect to x times dx plus the partial of u with respect to y times dy, dy. We'll do this for each thing it depends on, plus partial of u with respect to z times dz plus partial of u with respect to t times dt. And when I look at that expression, I say, oh, okay, well that's fine, because whenever I see this negative, this partial with respect to x, I know that's the negative of the conservative of the force I'm analyzing, which in this case is F. So in that case, I know that I have minus F, in this case Fx dx, plus a negative Fy dy, plus a negative Fz dz, and I recognize that that is F dot dr. Negative F dot dr. And then I still have this term out here. So plus partial of u with respect to time times dt. Well, from my work kinetic energy theorem, I know if this is the only force acting, that the work done by that force must be equal to the incremental change in kinetic energy. So wherever I see that work, I can think dt. And now I still have this extra term here. Okay. And now I realize I can go ahead and add dt to both sides, and what I'll have is the incremental change in u plus t is equal to partial of u with respect to time times incremental change in time. And that's really the expression that I wanted, because this guy here on my left-hand side is mechanical energy. And so in this case that I have a force like this that's acting, I don't have exactly like an isolated system, so you might think, oh, maybe you can't even use conservation of energy or work energy theorem. It's all just too confusing. Well, guess what? You still can. Because even though those relationships aren't going to hold, this one will. And we want to use these considerations as much as possible. You guys probably remember from 240, 250, we want to use energy considerations as much as possible. Why? Anybody remember why? Why does everybody like the energy unit?
Because conservation.
I feel really bad. Is it me? Am I like being weird today?
No, I
You
think
can answer me honestly, because you guys are just staring at me like I'm not here. But, okay, do you guys remember the energy unit? You guys remember what was good about it? All right, talk to your neighbors about the energy unit. And I'm going to go back and come back here. And, all right, why do we want to use energy unit?
energy conservation.
I think so.
That's why I think it was easy, because then it was like really easy to figure out what's wrong.
Because then it was all conservative.
Yeah.
Yeah, and
It doesn't feel like it's always
I know, plus, yeah, it's like,
What is it, conservation?
yeah,
of
the energy won't.
What's the
chemistry, or what was it called?
Joules is...
Mechanical
That's what I'm trying to think.
Oh, yeah.
Is it because like energy is always
Kilogram meter, which is
you'll never not have
square times...
Hopefully just goes so it's just really sensitive.
Yeah.
like yeah,
Not really applicable.
Just conservation of energy?
No,
Okay.
but that's a good try, and I appreciate you talking to me.
Yeah.
I'll take it. If you're going to talk to me, I'm going to say thank you. Does anybody remember? Because you had conservation of momentum, too. Why is conservation of energy nicer than conservation of momentum?
I'm going to take a shot in the dark and say that you can use conservation of energy across every single field of physics. So if you're going to be changing
Well, that's
doing
very
one type
true.
of work.
That's true. And that's definitely true. And I'm talking about something way less deep than that. Because it's like just why, if you could do it with momentum or energy, why would you pick energy? Let's say you could do it with momentum, Newton's second, or energy. You're going to pick energy. Why? Conservation momentum is how many equations? How many equations is conservation momentum?
One?
No. How many things have to be equal for momentum to be conserved? I think it's me. I should have gotten my
No, it's mid-semester,
You guys are
like,
just like,
No.
don't know what I'm talking
current.
about. It's 3 equations. Conservation momentum is 3 equations. Right? Is that right? I don't know. All right. Anyway, just give me one thing about energy that's nice. Another thing besides what Brian and Darcy have already offered. It's
That it includes mass,
does, yes. That's true. That's true.
where the momentum,
And there's something about that that is nice. What is mass? What kind of quantity is mass?
Scalar.
Yes. So why do we like to use energy? Okay. All right. So anyway, energy is a scalar quantity, right? So if E final equals E initial, it's one equality between two stupid numbers. For momentum to be equal, you have to have three things to be equal. For F equals ma, you have to set up three different equations. X, y, and z, they all have to be equal for it to be equal. Or r theta phi, they all have to be equal for it to be equal. Right? So if possible, just in terms of logistics and the life of an undergraduate, if you want something to take a third as much time as it would using other methods, you'll use energy. Okay? That's it. So this is why this can be useful, because you might say, well, it seems like if this were the situation, why wouldn't you just use F equals ma? Because this looks like a lot of trouble. I mean, energy's not even conserved. What the heck? Well, there's a reason to do that, because we like to use energy considerations where possible, because it is just tiny effective. That's all. All right. So, all right. I think I'll talk about an example here. And this will just be sort of a conceptual example. So let's imagine that you have like a Van de Graaff generator or something. So maybe this is like a positively charged object. And let's say that you're just going to stand here and hold this other positively charged like wand. And you're just going to hold it still. All right. And then what we are going to do is we are going to let the charge here sort of drain to ground as, slowly. Maybe we'll put a resistor in there. So that Q will slowly go from some big number down to 0. All right. So what's going to happen here? I'm holding this charge on a wand, so it's not going to move at all. So will any work be done on it? Can any work ever be done by holding something still? By anything? No. Okay, so there'll be no work done on it. And initially it started off with 0 kinetic energy because I'm holding it still. And initially, what kind of potential energy did it start off with?
Gravitational.
Well, that's true, but I'm more interested in, for instance, is it due to the presence of this big charge here and the little charge on your wand, there's potential energy there, right? Okay. So I'm going to ask you a question, and I'm going to ask you to talk to your neighbor. I'm going to ask you to actually answer me every single group. What is the sign on that potential energy? So take a moment and talk to your neighbors. Break the ice. Reintroduce yourself to your neighbor. All right. Is each group ready to be called upon? Okay. So go ahead and hold your hand up in front of you. If you thought it was positive, put your thumb up. If you thought it was negative, put your thumb down. Okay. All right. So let's go ahead and think about this. First of all, what would be a reason for this? The reason that is anybody willing to defend their answer? Yes.
Well, I kind of related it to gravitational potential energy,
Yeah.
where it wants to be pulled together, so you'd be closing a distance
Yeah.
in that case. So this is the opposite, because you've got two positive charges, so they want to push apart, so it'd be possible.
So instead of getting caught in a well, you're sort of up here.
Yes.
Okay. Anybody else have another thing they want to add to that? Although that's very good. So yes, perfect. So in this case, we have a situation where we have a potential energy, U, that sort of goes like that. So the closer they come together, that higher the potential energy is. And in terms of what's going on with the sign, it has to do with something we're going to talk about later in the hour, which is the direction of the force. When this, and it's sort of, when you look at this, this is a potential energy diagram. And we often make the analogy of the potential energy diagram and a roller coaster track, because, or a bowling ball on a hill, because they behave the same way. That means that if I were to take my positive charge and place it here and release it, it would fly away, because there's a repulsion here between these two. And so what that means is that as my slope on my potential energy diagram is a negative number, my force is this is my slope with respect to x. So let's note that du dx is a negative number. So that means that the force that's associated with this potential energy is x component is a positive number, because it is equal to the opposite of du dx. All right? So because I know that they were going to repel each other, it must be that the potential energy, and I know it gets greater in magnitude as they get closer together, because I have to do sort of work to do that, that this is my potential energy diagram. All right? So anyway, so I've got this initially, let's remind ourselves what's happening here. I'm holding this object at rest, so there's no work being done. I'm holding it at rest, so its initial kinetic energy is 0. Its final kinetic energy is 0. I'm letting Q drop, so which is why this electrostatic force is varying with time, because it is proportional to capital Q. And if you're wondering, it's Q over R. All right, so now when Q drops to 0, what will my potential energy be? 0. And my initial potential energy was some positive number. Positive number. All right. So this is one of those situations in which clearly energy was not conserved. We often think of the electric force as being conservative, but it is not conservative in the case that the field, and therefore the force, has a time dependence. All right, that's all I wanted you to think about. All right, so, but nonetheless, we have an energy relation, which is here, that we can use, and we should say yay about that. All right? Yay. Don't have to do vectors if you don't want to. All right. So let's talk about energy in the linear one-dimensional system. Okay. The thing is, I should be very clear that this is actually going to just be applied to what we will call one-dimensional systems. It really should just say one-dimensional systems, because we go beyond that. And what we mean by one-dimensional systems is we mean mathematically one-dimensional, not physically one-dimensional. So it means a system that for which location can be specified by a single parameter. So, sure, this is going to apply to an object that is constrained to move along a straight line, but it's going to apply to other things too, which we will get to. Let's first start with that object constrained to move along a straight line. So an example of this might be a train on a railroad track or something like that. Maybe a car on an air track in a physics lab. some sort of thing. So it looks like this. We have our path to which our object is constrained that we'll call the x direction. And we have, maybe our object is, one of those little carts from our physics lab. So we started off with some x initial, or x1, and we moved to some value x2. So here it's moving along. All right. So if I want to think about the work done by force on the system, I do not have to think about motion in the y or components of force in the y or z directions, because the object doesn't move in either of those directions. Therefore, there can be no work associated with components of forces in those directions. So whenever I have this situation, the work that's done by the net force on my object and moving from location 1 to location 2 is going to be equal to the integral from x1 to x2 f sub x, which will now be a function of x. So just to be very clear, I'll put that like that, dot dx, well, times dx. All right. So for right now, we're going to think about the force here, the net force, whose x component is written here, is going to be conservative. And this, what that requires for that to be conservative is that the force is a function of location. I've already written it as a function of location. It also requires that the work done in going from one point to another point is path independent. And whenever a function, a location can be written as a function of one parameter, it is always path independent. And there's a derivation of that, a proof of that in your author's book, but I'm going to save myself a few minutes and not do it right now because I don't know where my hour went. But that's not a hard thing to show. So whenever there's a force that can be written like this, it for a 1D system, a mathematically 1D system, it will always be conservative. Okay? All right. So this is conservative. And because it is a function of just my one parameter, and my system is one-dimensional. That's sufficient to make that statement. And I think this is page 2. All right. So again, if you want to see that proof, check out page 124. All right. So graphs of potential energy. Are something that we've always found useful. They're very great. They build your intuition. And now, because our location can be described with a single parameter, these graphs will just be very easy to present in 2 dimensions. You'll have u as a function of your parameter and your parameter here. Okay, so you can easily plot u on a 2D graph, and I think that's all I wanted to say about that. So let's go ahead then and talk about, well, I guess I should remind ourselves that we have an expression for work here. Therefore, we'll have an expression for u for the one-dimensional case. It is minus the integral of the conservative force, which if the net force is conservative, it could just be net force, sub x dx from wherever we're calling potential energy 0 to x. All right. And for the purposes of this conversation about 1D, we're going to let Fx just be the net force in the x direction and assume that there are no non-conservative forces acting so that the system is isolated energy-wise. Okay, so let's do the example of the spring. Okay, the spring's kind of a classic. I'm going to draw a situation. So maybe I have a spring kind of connected to like a wall or something like that. And it's kind of got like this little surface here. And something touches it, it can compress it or whatever. And then I'm going to imagine that maybe a mass slid in and compressed that spring a little bit so that it's resting against it. And there it is with that mass N. Okay. So what I know for a spring is that the force, in this case, just I've confined it to one dimension, so I only have an x component, but it's equal to minus kx, where I had to define x equals 0, and I'll do that. Let's imagine that this is the equilibrium position, so that when x is positive, obviously the force is in the negative x direction. Okay, so in this case, let's go ahead and find an expression for u of x. This expression here minus the integral from x naught to x of the force, which is minus kx dx. And I'm going to go ahead and let x naught be called 0, like I did in my figure. And I've got two negatives, so that's positive. And I've got k, and then I've got x squared over 2, which I had to evaluate from 0 to x, which just gave me that expression for u of x. And if I'd like to, I can make a plot of u as a function of x as this object compresses the spring. And the plot looks like that. It's quadratic. And what's the slope on this plot? Is it positive or negative? U as a function of x, its slope. It is positive, so what will be the direction of the force? The opposite, right? So you can draw a little plot here if you wanted to for force as a function of x. It will always be a negative number because that slope is always negative, and it gets more and more negative. All right, so that's one example. Another example that is useful is the roller coaster. Because the roller coaster is the first example of an object that, or of a system that is a one-dimensional mathematical system, but it is indeed physically a two-dimensional system. So here I have a drawing from the side of a roller coaster track. I'll use the same thing as your author. Something like that. Okay. So, and here's my x-axis, and here's u as a function of x. The cool thing about roller coasters is that they're just moving in gravity, and so u is proportional to height. So you can sort of just take a picture of the roller coaster, and you kind of have a pretty good plot of potential energy as a function of location. Now, this obviously isn't a one-dimensional thing, but mathematically I can determine exactly where my roller coaster is because I have a fixed shape to my track that if I'm at some location x away from wherever I'm calling x equals 0, I know exactly where I am on my roller coaster because there's a fixed value of y for each x, right? So this is still mathematically one-dimensional, all right? You guys okay with that? All right. So what that means is that I can think about this guy, this potential energy diagram, and I know that the x component of force is equal to minus du dx. So that tells me that in all these cases where the slope of u as a function of x is positive, if I were there, I would be pushed into the negative x direction by the force. This is my force. This is my line tangent. It's not supposed to look like a vector. It's just supposed to be my du dx. The slope of that line is du dx there. So in this case, the slope of du dx is negative, so the force is in the positive x direction. Here, du dx is 0, so the net force at that location is 0. Here, du dx is also 0, so the net force at that location is 0. Those have special names. Your book calls them x3 and x4. x3 is a location of stable equilibrium. It's equilibrium because at that location the force is 0, so it will not be accelerated away from being at rest at that location. But it is stable because if I were to deflect slightly, I would be pushed back toward that position. So what that means in terms of math is that d2u dx squared, oopsie, is greater than 0. So I'm curling it up, and that's what's making my equilibrium stable. X4 then is conversely a point of unstable equilibrium. And the condition for that is d2u dx squared. Clearly it went from something positive to something negative, so the second derivative, which is the derivative of the slope, is less than 0. So if you ever find an equilibrium point, which would be a point where du dx is 0, and you want to know whether it's stable or unstable, you have to take a second derivative. Okay. And this is kind of cool because, you know, like I said, in a roller coaster you just have gravitational potential energy. But you could have this potential energy diagram for an object confined to a straight line. Let's say that I had some sort of a bead that was connected to a straight wire, and it had some positive charge on it. And at this location here, corresponds to that, I have a source of field, that's a source charge of 4q. And at x4, I've got something a little less, maybe it's 3q. You know, it's not exactly right there on the wire, but it's near the wire, and this bead is confined to the wire, so it's going to move just like that roller coaster did. It's going to have a very similar potential energy diagram. Do you guys see that? When they're close, potential energy is going to go through a peak. All right? Okay. So that sort of thing. All right. And one of the nice things about energy is that you can, for this one-dimensional case, you can use energy to solve for motion, only in the case that you have one-dimensional problem. So we can find a complete solution of the motion. By reminding ourselves that kinetic energy is 1/2 mv squared, which in this case is x dot squared. And that is equal to mechanical energy minus potential energy. And u will obviously be a function of location. So in the case that we have a system that is isolated energy-wise, such that E is a constant, I have an equation here that I can solve for x dot. It is 2/m E minus U, quantity square rooted. And I would like to solve this for x as a function of time, and it's not exactly clear how to do that, so I want to illustrate to you how we do that. In order to do that, we remember that x dot is dx dt. And I can do separation of variables on this that will give me dt is equal to 1/x dot dx. All right. And that's what I'm going to want to use, where x dot is expressed here. So I'm going to integrate both sides from initial to final. And I'm going to get t final minus t initial is equal to my integral from x initial to x final of x dot of 1/x dot, which is square root of m/2 times, let's do it this way, e minus u to the minus 1/2 dx, because those things depend on x. You know how to do that integral. So once you do this, and maybe you'll call t initial 0, that is customary, you'll get t as a function of x. And you'll be able to perform this integral. Hopefully you'll be able to do it analytically, but if not, you can always do it numerically. So you'll be able to get t as a function of x, at which point all that you'll have to do is algebra to get x as a function of time. So in the one-dimensional case, we get to use energy, which is nice, and we can actually solve for motion. All right. Now, we're going to also talk about other systems that are curvilinear. So I'm going to pick up, I'm going to give you a quick preview of what we're going to do next time so that you can read it before you come. Curvilinear systems that are still one-dimensional. So in this case, we're going to be talking about maybe you have some sort of thing like this, which is a wire, and let's say that you have a bead sliding along that wire, so that initially we would call this the origin. And as the bead moves along that wire, the distance that is moved along the wire, maybe at some later time it's here, that distance we'll call it S. It's a path length. And we will work within this variable S because location will depend only on that. And as a result, have a one-dimensional system that we can do energy problems with. And then we'll also see that we can apply this to other systems that, again, don't look like one-dimensional systems. Let's say that you have a cylinder that we're looking at its cross-section. And we have a cube that we're going to place on that cylinder. And we would like to think about what's going to happen to that cube. Well, you can describe the location of that cube, again, with just one variable. So there are going to be lots of different systems that we can boil down to one-dimensional systems, even though physically they are of multiple dimensions and, three-dimensional systems. We can take it down to one variable. So we're going to do that stuff next time.
The second problem I saw that dolphin yeah.
What do you mean?
The second check.
Yeah, what do you mean?
I started so when you do the first check, which is yeah.
Can't figure out one of the directions. Column vector. I don't think, well, you couldn't
If I wanted to give that function an equation, I could have to be piecewise.
So you're going to, yeah, you could do it that way. That'd be fine. Just if you said for the second.
It's nice.
Oh,
Did he just
Did
do like depth elimination and just solve for each of these?
No, you just. So you
Yes.
have
Oh.
alpha is equal to whatever the top. I want to do whatever the top is.
Oh,
And
okay.
it's just like A plus B, right?
I
And then you
got
have the alpha to the B. So then alpha, and then A is equal to what?
Here goes.
Alpha 1 minus alpha 2.
Yeah. I got you.
You just
I
gotta
got
like
you.
look at it and set it.
Okay, right.
How
I
would
got
you
you.
have?
I got you. That's all I need.
Let me talk to Chris first and I come back to you. Did you get added? Because she asked me a question, I answered it, and then I don't know. Did you try going into Blackboard to see if you're in the class or not?
I haven't seen it on Blackboard. I'll check. I'll go check it now. But no, I was gonna say I was taking care of mine during Friday since like last Wednesday, so that's why I'm missing class. Friday and Monday. So, but
Is he on
it's him and his girlfriend. They go to the hospital together all the time because they have nothing else to do.
And they find stuff
Well,
wrong
she
or?
had to have operation, and he's like $1 billion.